So we'll go over chapter 8. We'll start the review on chapter 8, and the chapter 8 starts with a reminder of what homogeneous and heterogeneous mixtures are, and then it continues with the definition of a solution. So, what is a solution? A solution is an homogeneous mixture that contains small particles. Homogeneous. So remember how homogeneous means a mixture that you know it's made of several substances. That's why it's a mixture, but it looks like one. You cannot tell that there is more than one substance in there. So then it's homogeneous. It looks like one. It looks like the same throughout, and you cannot tell there is more than one substance. And heterogeneous, the other term, heterogeneous, means you can definitely tell the different substances within the mixture. So a solution is an homogeneous mixture, and people always think solutions are liquids, but they're not necessarily liquids. They can be gaseous or solid. So for example, brass is a solution. It's a solid solution made of zinc and copper mixed at the atomic level, and it looks like a new metal, but really brass is a mixture of two different metals, copper and zinc, but mixed so well at the atomic level that it looks like a new metal that we call brass. So that's an example of a solid solution, for example. A gaseous solution would be, for example, air. Air is the typical example of a gaseous solution, right? You have a mixture of several gases, and mainly it's nitrogen and oxygen in air, but there is also water and carbon dioxide. But you know, we don't know when we are looking around us that air is made of more than one gas, and we cannot even see it. So that's why it's an homogeneous mixture. It looks like one gas that we cannot see already from the start. So in a solution, and it's true that this chapter will all be about liquid solutions. When you have two substances only, the substance present in the lesser amount is called a solute. That's the name for the substance in the lesser amount. And then the substance present in the larger amount is called a solvent. And so you can think of, for example, when you are cooking, you put salt in water. So you're making a solution. And salt would be your solute, and the water is your solvent. But if, for example, you have a spoon of salt and you are putting just one drop of water in there, then the solvent would be your salt and the drop of water would be your solute, right? It's all a matter of proportions. Solutions with water as the main substance are called, and maybe you can tell me, there is a word for that. It starts with A. So solutions where water is the solvent are called, it's called aqueous. Aqueous. Yeah, aqueous. I'm sorry if I don't pronounce this very well, but aqueous. It's the name for, so we would call it an aqueous solution. Aqueous solutions are solutions where the solvent is the water, right? Water is the solvent. So there's many kinds of aqueous solutions, and that's what we mainly use because water is readily available. So a lot of solutions are actually made of what, you know, water as the solvent. So here, give me an example of a colloid. So let me tell you what is a colloid first. Colloids are homogeneous, so they are also homogeneous mixtures with larger particles than solutions, and opaque appearance. They have an opaque appearance. Opaque means it's not transparent, right? Opaque doesn't let you see through it. It's blocking the light, blocking visibility, right? So colloids are homogeneous mixture with larger particles and opaque appearance. And so examples of colloids would be milk, for example, is a typical example because it's opaque, right? You cannot see through milk. It's made of, water as the base, as the solvent, but then there are proteins, lipids, lactose. You have a lot of big molecules in there. So that's a colloid. But colloids are also like mayonnaise that you find in the stores, right? Any kind of mixture like that is creamy and that you cannot filter. You cannot separate the component by filtration, and they don't settle down. It stays emulsified. So like creams that you found in. Let me find a word for that. Moisturizing cream, for example. Moisturizing cream, right? Those things you find in the bathroom. A lot of those things you find in the bathroom that we use in the bathroom are colloids, right? They are opaque, but they are homogenized. They are emulsified, and they stay like that. They don't settle down. You don't have the larger particles settle down at the bottom. It does not happen with colloids. And at the same time, if you would filter, everything would go through and it would look the same through the filter, right? So that's what colloids are. Sorry. Sorry. Okay, so now suspensions. What are suspensions? Let me go here. Suspensions are heterogeneous mixtures. Heterogeneous. So you see the word here, heterogeneous. That means you can tell it's a mixture of different things because you can see the different parts. You can see the different substances. So that contains large particles suspended in a liquid, right? So particles are large, and because of that, they can settle down. So in the case of a suspension, settling down will happen. If you let it rest, the suspension, you will see how at the bottom you have the large particles, and then the liquid above will be thinner, if you will. And so suspensions can be filtered. You can filter or separate the particles from the liquid using a centrifugation or filtration. And so examples are, so in your lecture, blood is given as the example because blood has a lot of cells, right? Red blood cells, white blood cells, platelets, and then there is the plasma, and the plasma is mainly water, but there's all these cells, living cells in blood that are too big and that could be filtered, or at least when you are centrifuging the blood, and that's what they do when they no, it's not So yeah, I was saying that when you are drawn blood, they put it in a tube, and then they put the tube in a centrifuge, and then with the speed of the centrifuge, it accelerates the settling down, and the particles that are heavier or more dense, they will settle down at the bottom, and so that's going to be the red blood cells at the bottom of the tube. Then you will have different layers of white blood cells, because not all white blood cells are the same. You know, there are the leukocytes and lymphocytes, and so they have different densities, and so they will form different layers, and you can see the interface between the different white blood cells layers. And then on top of that, you will have the plasma. So that allows you to separate the different types of cells from blood using centrifugation. So that's a suspension. Other example could be simply, you know, sand and water, you know, sand and water, very fine sand. So if it's well mixed, you know, it's a suspension, but then if you let it rest, the sand will definitely go down and settle down at the bottom of the container, for example. So anything that has larger particles into a liquid will be a suspension. And there's many examples of that, you know. So that's how we can differentiate solutions from colloids from suspensions. So solutions compared to colloids and suspension, they are homogeneous and they are transparent when they are liquid. Because colloids are homogeneous mixtures too, but they're opaque. You have to think a colloid does not let you see through it. And a solution, because the particles are so small, it lets you see through it, and it looks like one substance, even though you know it's made of more than one substance. So, okay. And then the chapter after that goes through the properties of electrolytes and non-electrolytes. So, by definition, an electrolyte is a solution or something in solution that can conduct electricity. So it allows the electricity to be conducted because it has charged particles. So we call those ions, right? Typically, if you have ions in a solution, they are free to move because they are in solution, and so they are, you know, surrounded by molecules of water typically, if the solvent is water. And so they can move. And if you put electrodes, an anode and a cathode in the solution, and you have an electrical circuit, you know, from the anode to the cathode, and if you have some current going through this, the ions will carry the electricity and move. You know, the positive ions will be attracted to the cathode, the negative electrons will be attracted to the anode, and this will allow the current to be, you know, conducted through the solution. And then if you have a light bulb to show if the current you know, goes, then it will be lit. The bulb will be lit. And a non-electrolyte is a substance that has no charged particles, so only neutral molecules or anything that doesn't have any pluses or minuses, right? So then there is no way the electricity can be conducted. So that's why it's called a non-electrolyte. It cannot conduct electricity. And then there are two types of electrolytes. There are the strong electrolytes and the weak electrolytes. And a strong electrolyte means that whatever you put in water, typically water is the solvent, it will completely dissociate and become ions. So you have a lot of ions in solution, and it strongly conducts electricity. In the case of a weak electrolyte, the part, you know, the substance you put in the water only partially dissociates into ions. So you have and typically that would be a molecule, a neutral molecule. Parts of it are, breaking apart into ions, but most of it stays as the neutral molecule, and then it carries the electricity a little bit, but not very strongly. So that's why it's a weak electrolyte. But let's look at those examples and see what it means. So the first illustration here has, so water is in the background. Hopefully it's clear enough for you, but water is in the background, and then you have those chloride ions, the green balls, and then the barium 2+ ions, which are the gray balls. So can you tell me if this is a strong electrolyte, a weak electrolyte, or a non-electrolyte? So, okay, let me rephrase that. According to what I just said, do you think it can conduct electricity? So tell me yes or no. So can this conduct electricity? Yes, right? It can conduct electricity because you have ions. And it's only ions. If you look, it's only the Ba2+ and the Cl-. There's nothing else besides water. It's only those ions. So this would be an electrolyte. It can conduct electricity. And it's a strong electrolyte. So let me emphasize that it's a strong electrolyte because if you look at, so A, let me do A here. A is the first illustration here. A is a strong electrolyte, and it's so can you help me find the formula from Ba2+ and Cl-? When you put them together, what will be the formula? So it's an ionic compound. Yes, it's BaCl2. So that's the formula of the compound when it's it's a solid, when it's not dissociated in water. It's a solid. And so when placed in water, and let me insert, let me do it with this actually, this. So BaCl2 okay, BaCl2 is a solid. And when you place it in water, and here I need an arrow that where I can write water above, here, H2O, right? Water is H2O. Oops. So if you place it in water, what happens? So, and this chapter also has you learn how to use the solubility rules, but one of the labs had you also used that already. The solubility rules are tables that allow you to see if a compound is soluble or not. Let me show you that in the reference. So if you go into page 3, so the page where you have the list of polyatomic ions, and then below that there is a table called solubility rules. Solubility rules allow you to decide if ionic compounds are soluble in water or not. This is for water. And so if you look at the first part of the table, the top part of the table, it says soluble ionic compound, and then it lists ions, and there you have Cl-. Cl- is the third down, and it means that any compound made of the chloride ion is soluble, except, and there are some exceptions, except when it's with a silver plus, mercury 2+, and then lead 2+, right? And here it's with barium, so that means it's soluble. So if I go back to my review here, then I know it's soluble when you place it in water. And so when it's soluble, an ionic compound will dissociate into the ions it's made of. So here we already know because it's shown above, but when you undo the formula, you can retrieve the ions. And here, Ba is a predictable ion. And let me show that in the periodic table here. Ba is a predictable ion from group 2A. So we know it's Rs2+. It's a positive ion because it's a metal. And then Cl is an halogen from group 7A, and it always makes a -1 ion because you do 7 minus 8 and it's -1. So we know the formulas of those two ions from their position in the periodic table. So we can then write them that it gives Ba. And so the physical phase then is aqueous because it's soluble, plus Cl, and Cl is -1 in a superscript Aq, right? So Aq, when you have Aq as the phase after the symbol of the ion, means it's soluble in water. It's, you know, surrounded by molecules of water. So this is called the dissociation reaction of BaCl2. So BaCl2 is an ionic compound, and when you place it in water, here it's with the arrow that shows water is or it is added to water, and then it becomes the Ba2+ ion and the Cl- ion. Oops, it's not balanced, right? How many Cl- ions should I have? Yes. So it's very important here to pay attention to the number. And here we have 2 Cl- for 1 Ba2+, because the formula says Ba, and there is a subscript of 1, so it's 1 Ba2+, and then Cl2, which means you need 2 Cl- to cancel the two positive charges from the barium. So that's why you need 2 chloride ions per barium ions. And so that's what a strong electrolyte typically looks like. Its dissociation reaction shows that it's a single arrow to the right. That shows that it becomes only ions. So that's a strong electrolyte. Now let's look at illustration B here. B, it's CH3OH. CH3OH is methanol. It's you know, an alcohol to not drink because it really can get you crazy. It's very toxic. And so methanol, when it's in solution, stays as methanol. And here it's just methanol because methanol is a liquid. So you could tell from just methanol here, can you tell me if it's able to conduct electricity or not? So tell me yes or no. Yes, it can conduct electricity. No, it cannot. So if it cannot conduct electricity, and you're right, it doesn't, it's a non-electrolyte. Methanol is a non-electrolyte, CH3OH. CH3OH is a non-electrolyte because it is a neutral molecule. Because it's a neutral molecule, it's not charged. There is no positive charge or negative charge that would allow it to be attracted to the, you know, electrode of the electrical circuit. So it's not going to conduct electricity. And so we don't have to write the dissociation reaction, but In water, it would be aqueous. So let me just do something. So what would happen is that CH3OH, let me this small, a subscript 3 is a need this to be H. So this, when it's by itself, it's a liquid, and when you place it in water, it's of course still a liquid, water. When you place it in water, it stays the same as, and I should just copy that. It stays as the same molecule. It does not dissociate into different parts. It stays as CH3OH. But now, because it's in water, we would change the phase to aqueous, right? Now it's a mixture made of water and ethanol. And that's why we would change the physical state to aqueous if it's not pure methanol. And so, because it stays neutral, it does not conduct electricity. And it's a non-electrolyte. So now the other illustration here is very poor quality. But okay, if we look at it carefully, there are two single red balls that have been labeled H+, two single blue balls that have been labeled F-, and then the rest are blue and red bonded together in a 1-to-1 ratio, right? And so when it's bonded together, F- plus H+, it's going to be HF. HF will be neutral because the positive charge from H+ will cancel the negative charge from F-. So it's HF. So can you tell me, is HF able to conduct electricity? Yes or no? Yes, yes, it is an electrolyte, but it is what we call a weak electrolyte because it has some ions. You have here 4 ions for a total of 5 plus 4, 9 particles. So half of it are ions, and half of them are neutral neutral molecules of HF. So it conducts electricity, but weakly. So let's write the dissociation reaction. And so HF is, you know, it's a gas actually. When by itself it's a gas. Well, let me write aqueous because we will do like if it's already in water. And notice how I will choose an arrow that is a double arrow. There's not much choice, but here let's use this one because then I can put in water. When HF is in water, it's a double arrow, and that's what you will learn in chapter 6 that comes after. So that's why I have to tell you about this. When you have, and double arrows in chemistry are not written like this, but that's what I have available here. We would do them just like we normally do them, and then another one below, you know, parallel to it, but pointed the other way. So double arrows tell you that you have a reversible reaction, which means it goes from left to right, but it also will go from right to left. So it goes back and forth between the two sides of the equation. And so here, let's complete it on the right side. So HF, when it's in water, it dissociates into H+, and it's an ion in a solution, in aqueous solution here, plus the F-. Let me get this. So F-, and that's also aqueous when it's in water. But notice here, and the key to differentiate a strong electrolyte versus a weak electrolyte, it's the arrow. It's all in the arrow. So it's really a detail that you have to not overlook. A weak electrolyte has a double arrow that says, yes, my molecule is dissociating into ions, but the ions also get back into becoming the molecule. And that's why you have a mixture of both, of the ions plus the neutral molecule. It's not, it's what we call a reversible reaction, and it happens both ways. And so that's why you have both the ions and the neutral molecule. And then because of the fact that you don't have enough ions to strongly conduct electricity, then it's a weak electrolyte. It weakly conducts electricity. So that's it for the electrolytes. But here I insist a bit on electrolytes because it's important to be able to write those dissociation reactions. It's recalling the knowledge from chapter 3. So NaOH is a solid by itself, as a pure substance is a solid, and you can place it in water, it will dissolve, and it's a strong electrolyte when dissolved in water. And so let me show you the solubility rules briefly here. So NaOH, when you have Na plus and OH minus, here there is no Na plus listed in those ions. So you have to go down to here, OH minus at the bottom of the second part of the table. Here is listed among the insoluble ionic compound. So whenever you have OH minus, it typically makes insoluble ionic compound, except there is important exceptions here. If you look at the line of OH minus, it says compounds of the alkali metal cations and NH4+, that's ammonium, calcium, strontium, and barium are exceptions, which means they are soluble. And the alkali metal cations, the alkali metals cations are those from the group 1A. Remember, we call them alkali metals. Hydrogen is not a metal, it's a non-metal. It's an exception from this group. But all others, lithium, sodium, potassium, rubidium, cesium, and francium are all alkali metals, and they always make soluble compound, actually. So NaOH is soluble in water. So let's write its dissociation reaction. And let's insert an equation here. So NaOH is a solid by itself. No. And when you place it in water, let's put an arrow where we write water above. So it's a strong electrolyte. So notice how I chose the arrow that goes only straight to the right. I didn't choose the arrow that says it's a reversible reaction. This is a strong electrolyte, so I need to use an arrow that only goes to the right and makes. So what are the ions when you have the alkali? Sodium. Sodium, we saw it's in group 1A, so sodium is a 1 plus, 1 plus ion, plus 1 ion, Na plus. And then its phase is, what happened there? Oh. Let me change that. Okay. Na plus, plus. And so we saw OH minus is a polyatomic ion, so it stays together like that. OH minus, it's called the hydroxide ion. and it's aqueous when you place it in water. So this is the dissociation reaction of a strong electrolyte because it only makes ions when you place it in water. Okay, so that's just to emphasize again what is a strong electrolyte. Well, so let's go through solubility now. And sorry, one of the for lab 5, you had to learn the fact that like dissolves like. So let me remind you here this basic rule of solubility: like dissolves like. And that's the rule you need to follow here to decide which compounds are soluble in water. Like dissolves like, which means polar, polar substance dissolves polar substances, and non-polar, substances dissolves non-polar. They have to be the same kind to be soluble together, right? So that's what you want to follow here. And so you're given LiCl. Let me look at something. Okay, LiCl. So anything that would be ionic or polar, so ionic as well, might be soluble. So for this one, you actually would want to look at the solubility rules. So let's look at the solubility rules for LiCl. If we look at the solubility rules, you have in this reference, and there are many kinds of solubility rules tables, so they may not look exactly the same, but they will lead to the same conclusion. So in the part where it says soluble ionic compound, we have Cl minus there, because in LiCl we have Cl. And Li is not listed there, so let's look at Cl. Cl minus makes soluble ionic compound. Let's look at the exceptions, except when it is with silver, mercury, or lead. And here it's with lithium. Li is lithium, so it's not an exception. So that means the LiCl is a soluble ionic compound. So then this, we can say that it's a soluble ionic compound, soluble compound in water. Let me rephrase that. Ionic compound soluble in water. Okay, so this one you can decide by using the solubility rules because it's an ionic compound. Now let's look at CH3I, right? The last letter is the symbol for iodine, right? So can you tell me, is this an ionic compound or a covalent compound? So tell me, ionic or covalent? CH3I. Is it made of a metal and non-metals? Or is it made of non-metals only? Yes, it's made of non-metals only, right? If you look at the periodic table, C is a non-metal. H, even though it's here, it's a non-metal. Please do not confuse that. Hydrogen is a non-metal. It's an exception here. It's part of the non-metals. And then iodine is also part of the non-metals, right? They are all, well, except hydrogen, but they are located to the right of the staircase here. So that means they are all non-metals. And whenever you have carbon, typically it's the backbone of a covalent compound. So that's a covalent compound. Now, when you have a covalent compound, to decide if it's soluble in water, you have to decide, is it polar or non-polar? So you know that carbon likes to make 4 bonds. So here you have 3 bonds with 3 hydrogens and 1 bond with the iodine. So let's decide if this is a polar molecule. And for this, you will want to look at the electronegativities. Electronegativity difference between C and H. You know, 2.5 minus 2.1 is 0.4. And this is considered nonpolar according to the middle table here. And C and I, because there is no IH bond, it's only C bonded to iodine. 2.5 minus 2.5, it's a difference of 0, so it's a nonpolar. So then what can we say of this molecule? Is it polar or not? It's nonpolar, right? It's nonpolar because there's no polar bond. So it cannot be a polar molecule because we have no polar bonds. So it's a nonpolar covalent compound. So what do you think? Is it soluble in water or not? So what you have to ask you, so water, is water polar? So you know that water is polar, right? Let me write this here. Yes, water is polar. Water is polar, which means polar dissolves polar, so it will dissolve if it is polar. But here we decided CH3I is nonpolar. It's nonpolar, so it won't dissolve in water. They will not dissolve well together. They will make 2 phases, you know. You will see like an interface. They will not mix well. And, you know, one will sit on top of the other. Most likely the CH3I will sit on top of the water. I don't know. We need to know the density value to know this, but so it's non-polar, so it won't dissolve in polar water, right? Water is polar, so because one is non-polar, water is polar, so they won't dissolve together. Okay, so let's look at the other one here. C5H12. Can you tell me, is this a covalent compound or an ionic compound? So tell me, ionic or covalent? Yes, it's covalent. It's covalent because it's made of carbon and hydrogen only. And carbon and hydrogens make covalent compounds. So now let's decide, is this polar or non-polar? So, you know, when you have C and only H's bonded to it like that, you have to imagine that it's a chain of carbons surrounded by hydrogens to complete their octet, right? It's just, if I, you know, while you think about it, I will just show you what it looks like. CH2, or let me do it in the so we have how many CH2s? 5, so let me write this here. So 2 more of the CH2. 1, 2, 3, 4, 5 carbons, and then 6 plus 6, 12 hydrogens, right? So that's the formula, or you know, the breakdown of the molecule. And so you only have carbon-carbon bonds and carbon-hydrogen bonds. And those bonds we've seen they are non-polar, right? Carbon-hydrogen, there is a electronegativity difference of 0.4, and this is considered nonpolar. So this is a nonpolar molecule. So will it dissolve well with water? No, it won't dissolve in water, right? It won't dissolve in polar water because water is polar, right? Water dissolves what is polar and does not dissolve what is nonpolar. Okay, so that's something you will need to use for your lab 5. Decide if your molecules are polar or not, and if they are mainly polar, because the molecules you have in the lab 5 are big. So if overall you have a lot of polar bonds, then you consider the molecule polar, and then it will be soluble in water. If it's mainly C-C bonds and CH bonds, then it's nonpolar. And then when it's nonpolar, it will dissolve well in oil because oil is nonpolar. Oil typically is made of molecules like that, like the C5H12, you know, molecules with a lot of carbons and hydrogens. So that's why they are mixing well together.